Hi, everyone. I'm Akshay. I lead the Reserve team here at Anyscale. And with me today, I have Neelay and Ryan over there who will be talking to you about NVIDIA and Triton as well. So for a long time, people have been asking us, what framework should I use, Triton versus Reserve? What are the benefits of each? And this year, we worked together with the NVIDIA folks to bring to you an integration so you don't have to choose anymore. You can get the best of both worlds with the performance efficiencies of Triton as well as the scaling and flexibility of Reserve. So for this talk, we'll kind of go over the high-level architecture of both Reserve and Triton, and then talk about the integration, how it was made possible, and what are the benefits for all of you guys. So first, I'll cover Reserve's architecture. Our original motivation behind Reserve was to build a very flexible and scalable framework for online inference. So what does that mean? We wanted to make it very simple for you to go to production, and then also handle things like auto-scaling and all the infrastructure complexities out of the box. So the one primary thing for Reserve was we wanted for it to be Python native. So just with a couple of simple decorators, you could go from development to production very easily. And then you could not just deploy ML models, but a full ML application. So that can contain your business logic, many different models chained together. And you can do this in one system with just simple Python decorators. So that was the simplicity was the big focus from the beginning. The other big point was how do we construct these like complicated multi-model type of applications very efficiently. So with Reserve, we added patterns such as model composition and model multiplexing. So for example, if you're building a recommendation system where you might have some business logic and then you might have an ensemble of models like collaborative filtering, some multi-arm bandit, and so on, you can declare all of these in one application and then scale each of these components independently. And they can even take different resources. So maybe your business logic can just run on CPUs, but your collaborative filtering model needs a GPU, and maybe your multi-arm bandit needs a different type of GPU. And you can do all of those together within Reserve and then scale these independently within the same service. So you get kind of these scaling efficiencies while also better operational maintenance over time. And the other aspect that's really cool is you can also do fractional resourcing. So if you have something that's very lightweight and just takes half of a GPU, you can declare a deployment that does half of a GPU. So now Reserve is in production and used by many large companies, and many data scientists, ML engineers, and ML DevOps folks love it to take ML models to production quickly. So let's cover some high-level concepts in Reserve. The deployment is the central component in Reserve, and that is the unit where you can declare your resources and scale, and as well as the auto-scaling configuration. So a deployment can consist of ML models or business logic, and then each deployment will scale in units of replicas. And these replicas could be located on different nodes in your cluster, and not all nodes have to have all kinds of deployment replicas. An application in Reserve can consist of one or more deployments. So this is where you can like put together your recommendation system with some fast API ingress, and then followed by a bunch of different deployments that get called through the inference call itself. Now, since like all these different deployments and replicas are not homogeneously located on all the nodes, you need some component which can route to different nodes and different replicas. For this, we have this concept of proxy, whether it's HTTP or gRPC, and these can do the load balancing across the entire cluster. And then finally, we have this component that will actually handle the auto-scaling and lifecycle management of these replicas across the cluster. This is called the serve controller, which runs on the head node. So each replica is constantly pushing its metrics to the autoscaler in the serve controller, and then as the serve controller sees the requests are kind of piling up, or the request rate is higher than your target, then it will scale the replicas up, and vice versa if it needs to scale down. So this is kind of the high-level architecture of Reserve. Now I'll ask Neelay to come on stage and talk about the architecture of Triton. And finally, Ryan will go over how we made the integration possible.
Thank you, Akshay, for that wonderful introduction. And as you mentioned, my name is Neelay, and I'm going to go over a little bit of the Triton Inference Server. Okay. So there's basically three main things I want you to take away about the Triton Inference Server. First, that it's part of I keep expecting to be behind me, but it's not. First, that it's part of an overall inferencing stack from NVIDIA, right? That obviously starts at the hardware accelerators, but it also includes optimized runtimes, CUDA as well, and then we get to the model serving part, right? So again, it's part of a larger stack. The second thing, it's all about trying to get the most out of your GPUs, right? So we have a lot of different batching techniques that's really focused on trying to really focus on single node performance, getting the most out of your GPU utilization. And the final thing is that it's really about taking your models and making them easy to deploy in an optimized way into your applications. And it's the last part that I'm going to really talk a little bit more about how we achieve that through a series of abstractions. So at the lowest level, we have what we call the Triton backends. These are essentially optimized runtimes for different major frameworks. Things like optimized versions of TensorRT, LM, VLM, Onyx runtime, even OpenVINO for running on CPUs. The major thing here to remember is that this provides the latest optimized libraries for NVIDIA hardware as well as other hardware. These are community maintained, so we work with other teams and other the framework maintainers to make sure that they are optimized. And the next thing is that it essentially gives you a unified API that abstracts the frameworks and the models from the rest of the system. So Triton is a multi-framework system. Interacting with an Onyx model looks the same as interacting with an OpenVINO model, looks the same as operating with a TensorRT model. And we really like that flexibility because it allows you to easily change models and change frameworks easily. So once you've built your entire stack, let's say for stable diffusion, which I'll show you later, you could easily move from a PyTorch model to a TensorRT model and not have to change anything about the rest of your stack. Next piece of how we do that is the Triton core. So as I mentioned, the backends are really wrappers and optimizations around frameworks. The Triton core is kind of the middle piece, right? It sits in between an application and the backends. So it implements various framework-independent optimizations, such as dynamic batching, such as pipelining between different models, really focused on zero-copy memory, making sure that the memory transfers don't go back to the CPU if you don't need to, right? Even if you're going cross-framework, we can make sure that we use a zero-copy between, let's say, a PyTorch model and a TensorRT model. It also offers state and version management, so you can update your models on the fly. So we have APIs around that. The other nice thing is it really provides a common set of metrics and tracing. So again, being framework agnostic allows you to build applications that auto-scale with a common set of metrics. If you change your model, your metrics don't have to change, and neither does your auto-scaling strategies. Final piece at the very front is the Triton front end. And as I mentioned, our whole goal is to really make it easy to take optimized models, optimized frameworks, and then integrate them into your larger application. And that's where the front end sits, right? So it's kind of a customizable piece. We offer out-of-the-box front ends for Kserve v2, which is kind of a microservice-oriented API. We have a generate endpoint that's more text-focused. We also offer front ends for SageMaker and Vertex AI as well. And there's a fairly easy, well-defined interface to write custom front ends, and that's actually one of the things that Ryan's going to talk a little bit more about. So I'm going to let Ryan come up and now talk about how we really got the best of both of these by integration.
So thanks, Neelay. Yeah, so Akshay and Neelay gave you kind of a high-level architectural overview of both RayServe and Triton. And for those of you who may be familiar with one but not the other, I'm going to do a bit of a deep dive on how they actually integrate at the technical or application level. So let's start off with the architectural diagrams you saw before. Essentially, on the top, we have the RayServe architecture that Akshay spoke about, and on the bottom, you have the Triton architecture that Neelay spoke about. And the main kind of connection layer here that we're looking at is RayServe's notion of a deployment, and how Triton interacts with that is through Triton's Python APIs. When you combine these two things, you get the best of both worlds, choosing sort of what you want from each. So from RayServe, we like the Python first, Python native approach, as well as the easy load balancing and scaling that you get through things just like a simple decorator. And from Triton, we like the things such as the optimized backends, the common interface, and the model repository that you can kind of take, use in Triton standalone, use in RayServe standalone, join them, etc. And when you marry these two things through this dotted green line, you get basically the fully compatible with RayServe's notions of model composition and these distributed pipelines, as well as Triton's in-process notions of a ensemble or model pipeline. So let's talk about that Python API box. So Triton has a few Python APIs. As Neelay mentioned, there's various components like the front end, the core, the back end. For defining your inference or your business logic, you'd probably start in the back end realm. So here is an example of Triton's back-end Python API. It's a pretty similar, simple interface where you just define a class and adhere to some interface, right? So you just need these three functions: initialize, execute, and finalize. Initialize and finalize are just sort of for cleanup and setup, but they're optional if you don't need anything. And then execute is where most of the magic happens, which is actually taking the requests that came through your pipeline, whether that was through some gateway or through RayServe or however you define it, doing whatever you want to it, and then returning responses ultimately back to the client or the application. Things that come out of using this Python backend API are a lot of the common technologies you probably see, such as metrics through a Prometheus format, tracing through an OpenTelemetry format, as well as like logging and trying to be optimal with how we move data around. So Neelay mentioned trying to keep zero copy as much as possible. The objects you're passing around here in the Python backend are very compatible with other frameworks, so taking like a Triton tensor, moving it to PyTorch, ideally with no copy if it stays on the same device. Or if you need to move from GPU to CPU for some CPU-bound operation, you can do that converting to NumPy or something as well. So this is all for kind of your business logic, how you define a model in a Python-centric way. But how do you actually take that and start a RayServe application? That would be this front-end API. So this here, import Triton server, is the bread and butter to how this integration works. This is primarily Python bindings to Triton's set of C APIs that you saw in the architectural diagrams. What this means is that you also get access to not only the Python backend APIs like we saw, but also all of the backends that Triton supports. And most of these backends are actually written in C++ and optimized for their various use cases or hardwares, etc. So even though you are at the application layer writing something in Python, it can ultimately go through Triton and C backends. However, at that layer where you're writing the code as the developer, it is somewhat Python native in that you can pass these dictionaries and lists directly as the inputs. So you can refer to the example on the right and see like the inputs, text input and stream. These are just Python objects, right? And then ultimately, when doing inference, we keep performance and larger scale pipelines in mind. So this inference is obviously not blocking. It can be an asynchronous operation where while you're waiting for Triton C++ backend to compute something, for example, you can be processing more requests on your RayServe frontend or doing some kind of pre or post processing in parallel. So given all that, how do we put these two things together? So many of you in the room here at the Ray Summit are probably familiar with RayServe. So you've probably seen this type of example where we have a deployment and we add a few decorators from RayServe, and we now have something that has all the great things that Akshay was talking about, like fractional resourcing, scaling, etc. The main differentiator here is in the initialize and implementation details, where we initialize Triton through the Python API I described, and everything else kind of just works, right? So now that you have a Triton object handle in Python, you can define your inference logic. We have an example generate function here that I'll go into more detail. But through a simple call to the Triton process API, you get things like the scheduling, the model management, and the inference layer from Triton, while also getting the fast API front ends, the deployment scalability, and just the ease of use that RayServe offers in Python. So let's walk through a bit of an example of how this looks. So vision models, large language models, these things are trending, they're very popular. One such example is stable diffusion. So we actually have an example here, end-to-end, going from stable diffusion taken in PyTorch, for example, bringing it through the journey, through whatever framework you like in Triton, ultimately turning it into an application and scaling. So on the right-hand side here, the first step for any Triton user is to prepare a model repository. This is just a defined structure for how Triton will read and manage your models. In this example here, you can see a model folder called Stable Diffusion XL, where for version 1 of this model, we have a few files here. At inference time, we actually only need one of these, and you can choose in this example. So we have XL engine batch size 1. This is a TensorRT model. We have XL 1.0 Onyx, and then we have the same for PyTorch. So the reason these are all here is to kind of tell you that everything is very customizable and flexible. So you can take a PyTorch model if you're happy with PyTorch, and you can run it through Triton. If for some reason you prefer Onyx runtime, you can convert through Torch export to get an Onyx model, still run it through Triton. Or if you want to really optimize for a specific GPU, specific batch size, certain parameters through things like a deep learning compiler, then you can use TensorRT. So you can kind of go this whole flow, PyTorch Onyx, Onyx TensorRT, take and choose whatever you like. But ultimately, you get this model repository, and then a configuration file that tells Triton what to do with it, which model to use, what type of resources to use, and what the I/O looks like to actually do the inference or form some kind of pipeline out of it. Once you have all that, and we have a tutorial here on the side, but once you have all that, then you can move on to the deployment. So earlier I showed just a high-level example, but this actually goes into some detail on what that generate function might look like. So what this function is doing is, in the context of Stable Diffusion, we're trying to generate images based on a prompt, right? So through not many lines of code, we can pass the requests that come through the generate endpoint exposed by RayServe, all the way through Triton calling TensorRT, and get back an image returned to the user through Fast API. Once you have that, this, like I said, this is a RayServe deployment, right? So you get all the tools that come with RayServe as well, including the RayServe CLI. So using serve run, we can launch this deployment, and going off the decorators that define the resources and options needed for the deployment, you'll get exactly that in your deployment. So there's actually a secret fourth step here because maybe this output is not exciting enough. So we can use it. And here's an example of generating pandas. So and not the data frames library, but the animal. So here we have an example client talking to the Fast API generate endpoint, where we request a scuba diving panda, and we get this image. And we can kind of take this as a fun example, but we can also profile it and see, take in a real application into mind. How do we actually benchmark and determine when we need to scale, how we observe our deployment, etc. So we'll look at that. So you may be asking, why would I go through all this work? Why would I want to embed Triton in RayServe or vice versa? And some of that is the optimized backends that we talked about. So in this example, we highlight the TensorRT backend running through Triton. Most of that is hidden away from you when you're writing your deployments and you're going through Python APIs. But through very minimal code change on the application side, we actually get about a 9 to 10% throughput improvement for this example of just generating images through a Stable Diffusion model. And this is just on single node, single GPU, single client. Not too shabby, but you may want to know, how do I scale this thing, right? So once again, this is where RayServe comes in. So just by changing the decorator that you apply to your deployment, you can define auto-scaling criteria and run with it. You don't need to make any changes to Triton's code. You don't need to make any changes to the inference code. You just redeploy with the same thing, and you get the load balancing flexibility that Ray offers. So we can run our same experiment and see how we do when auto-scaling. So that's what we get here. We scale up to, we defined a max of 8 GPUs in our deployment in the previous slide. And we saw actually a 45% improvement when you start to scale this up. So as you scale it out, you get bigger and bigger gains. You may wonder why this, if it was like a 10% improvement for one GPU, why is it not an 80% improvement for 8 GPUs? And that's just an artifact of the benchmark. So this one is actually including auto-scaling in the benchmark. So while the requests are coming, nodes are spinning up, GPUs are spinning up. And so it ends up being a net 45%. But if you were to take this standalone, pre-loaded 8 GPUs, et cetera, you'd probably see more linear gains. And now that you have a deployment, now that you've figured out how to scale, and you figured out how to integrate these things, how do you observe that deployment? Well, once again, Rayserve comes to save the day. So Rayserve has the dashboards that many of you are probably familiar with, and it consumes things like metrics in a Prometheus format. And if you remember, Triton has those metrics. Triton also exposes custom metrics if you'd like to add your own to your business logic or to your model. And you can view these all in the dashboard. So what this dashboard is showing is actually from the prior example, where we see that the deployment scaled up to 8 replicas. And then as the benchmark ended, it actually scaled back down. So to save you resources when you're not using it. And then you can observe all the replicas independently and sort of gauge the health of your deployment. So with all this, I'd like to summarize essentially, for Triton users, why is Rayserve interesting? For Rayserve users, why is Triton interesting? Maybe if you're either, they're both interesting to you. So I just highlight a few things here. If you're a Rayserve user, there's many benefits of Triton. So we have the example of the optimized backends and the flexible model repositories where given the same model, you can run on a framework of your choice as accelerated or not accelerated as you want it to be. You got the latest libraries in terms of like CUDA, cuDNN, GPU driver support that come in the Triton software stack. You get the in-process APIs that let you define things such as a in-process model pipeline. So maybe on a single node, you have an optimized zero-copy pre-processing compute post-processing pipeline. But then with Ray, you actually scale that to multi-nodes and have distributed pipelines of these pipelines, or have your models scaled out on separate nodes. Then for Triton users, you may ask, why Ray? So as we walked through in this example, you get that Python first, easy deployment developer experience with the load balancing and auto-scaling essentially just being a decorator in Python. You get the distribution of the pipeline through the Ray cluster, and kind of the quick dev cycle that you get out of Python, right? So maybe if you've used Triton, you've had to go through maybe some C++ code or some binaries in certain containers. But in this workflow, it's all Python. You can, kill your service, change a few lines, start it up again, no compilation, no builds, etc. And you're off on your way to a auto-scaling deployment of optimized models through TensorRT and Triton, for example. So with all of that, we have a few resources, and then I think we'll spend some time on questions. Thank you. Do we have a mic for questions? Or maybe raise a hand or anything? You guys want to come up? Yeah.
I'm curious, if you have only the combination between Rayserve and TensorRT without the middleman Triton, how much performance improvement you can gain from the bar charts you've shown earlier?
I can take this one. Yeah, so we don't have a direct benchmark, like you're saying, but sort of the goal of what we're trying to show is that, so in this example, we had a PyTorch, Onyx, and TensorRT for the same model, for example. Through Triton as the middleman in the Rayserve deployment, it's just a change of a flag in the configuration file, which model gets run. If you wanted to write that in process in the Rayserve deployment using TensorRT Python APIs, you'd have to go figure out how to write TensorRT code, figure out all that, and change your deployment significantly for each framework, right? So kind of the value we're trying to show is that you get that reusable model repository through a common interface where the code really doesn't have to change very much, and you just swap out based on your needs.
Yeah, Just also comment, I think that there's a lot of kind of engineering years that have gone into some of the back ends and the way they use the frameworks. So in a previous version of this, we did actually use Torch Compile with the TensorRT backend, but still saw performance improvement by using the TensorRT backend directly. So.
Hi, thank you for the interesting presentation. I'm a little bit new to this software stack, so I'd like to start my question from a little bit below level, from the infrastructure. Do I understand correctly that in order to run this stack, Triton plus Ray Serve, you have to have NVIDIA compatible processor architecture on whatever node you use? And also, a related question, can this be run in a container form factor? And if so, what is the compatibility? I'm particularly interested if you're compatible, let's say, Amazon Inferentia or Graviton and such. Thank you.
Yeah, so for running Ray in general, you can kind of run it on any hardware, like whether it's bare metal, VMs, or whether it's Kubernetes. And like most people in production tend to use Kubernetes for running Ray and Ray Serve. In terms of Inferentia and these other accelerators, there's also support for it within Ray. So you can have, instead of GPUs, you can have like Inferentia resource or like TPUs and so on. I mean, this talk obviously is for working on NVIDIA accelerators only, but you can extend Ray to work on any accelerator. Yeah, Triton. No, it doesn't. Okay, go ahead.
Yeah, so I mean, obviously Triton is accelerated for GPUs, but we also support CPUs, and there are like holistically, like Python models, for example, many of which can just run on Python on CPU. But there are even optimized CPU backends, like Neelay mentioned, OpenVINO, for example. And it's not like a requirement that you have the stack, so for example, we ship containers monthly with all the stack prepared for you. It's not a requirement that you have a GPU to run that container. It'll work with no GPUs on the system. And then for something like Inferentia, like a maybe custom accelerator that's not a GPU, Triton has examples for running Inferentia. So theoretically, composing these things should all work in harmony together. Yeah. Oh, sorry.
Hello?
We'll go with the mic wherever it went. Yes.
Do you recommend to use this for batch prediction? I mean, offline.
Sorry, could you repeat the question?
Do you recommend to use this for batch prediction? This is for online, right? So it's good for online. It's good for offline, like batch prediction.
Yeah, so I guess I can speak about Triton generically, and maybe Akshay can speak about Ray. But so in general, Triton's very configurable, and there may be certain backends or certain configurations that are preferred for something like an online scenario versus an offline scenario. But there's nothing limiting you at like the framework level to say like Triton is better at one than the other. So for example, like a large language model, for example, you may tune things about the model to prioritize something like time to first token, which might be more important in an online scenario, whereas you could separately tune the model for an offline scenario where you just care about throughput and you don't care about that latency, for example, right? Most of that would require not much or little, no change to Triton, and is more so model-oriented. And then I think Ray would have some similar concepts.
Yeah, for offline batch scenarios for Ray, we typically recommend Ray data. So that's more like that can handle batching more effectively, like kind of perform more effective, like batched offline data, map reduce operations, and without the HTTP overhead that you will have in like a request response framework.
How about VLLM, actually? How does TensorRT and VLLM actually? I do see some performance comparisons between VLLM and TensorRT showing higher performance in some cases. Do you have any comments on that?
I say in general, I think we're big fans of the VLM project. So Triton also has a VLM backend as well. And so you can run and get all the common batching and metrics and things like that, and then easily swap between VLM and TensorRT-LM. So I think out of the box, TensorRT-LM performance It requires some investigation and tuning. Generally, if you spend the time to tune it, you can outperform out-of-the-box VLM as well. But I think it's continually an arms race, right? With the LM space, I think both are moving very fast.
Hello. I have one question. It's clear for me when to use like Razer and Triton and all the wins it has. Is there any case where like you all recommend just to use like Triton standalone without combining it with Razer? Is there like any performance difference with using like Triton standalone instead of combining it with Razer?
I can give a generic answer to start. So, for example, most of this demo is focused, the interaction was focused on like scaling, for example. So if you know in your scenario, you're just running like single node, single GPU or something, maybe you don't need to add Razer into the mix to achieve the same goal. Maybe you could just run Triton standalone. For example, Triton has a set of like web serving front-end schemas, like kserve predict v2 or OpenAI or something like this. Maybe you want a custom schema or something for your use case. When you go through a Razer deployment, like when it has that fast API integration, you can define your own. I mean, you can do the same just with fast API and without Razer as well, but it's sort of weighing pros and cons. Like, there are clear benefits from introducing Razer into the mix, so are those things that interest you? If so, you can do it. If not, maybe it's one less thing in the mix for that particular scenario, but yeah, I don't think there's major like bottlenecks with the collaboration, for example. Yeah.
Oh, great. Is there any performance degradation when introducing Razer on top of Triton?
Sorry, could you repeat the
Yes,
question?
sir. If like I see you benchmark like the performance with like Razer and against like Razer plus Triton. I was wondering what is the performance of Triton standalone in that case, if you know the numbers. If not, it's okay.
Yeah, so we didn't run a benchmark for this example, and we're not like comparing directly. They may be different input formats, for example, when in this example versus like Triton's native front ends. So yeah, we don't have a number or anything to share yet.
Cool. Yeah, I think we're at time. So we'll hang out here if there's any more questions.